What we had done last time. Okay, no problem. If you recall, I can go back to the model, okay, that we were discussing right from our class 1, okay, and that model or system was, whenever I want to do some change in topic, I go back to my system, because all the time I am dealing with the system and I must work for the system. Clear on this, clear on this, clear on this. Okay. Sources we understand, the transport mechanism we understand, effect on the receptor we understand, and what we have done in the process, also we developed some understanding of source transport recept impact. Okay. So much is the quantity and this will result in so much of impact. Okay. If the impact is less than, okay, less than the burden which it can receive, okay. If impact is minimal, okay, what would you do? You will not do anything, everything is fine. Impact is minimum and if the receptor can accept that impact, you will not do anything. Okay. So then everything is fine, very goody picture, okay. But generally that will not happen. Okay. Receptor will suffer, oh, the emission is too much and all the problems are being caused about. Then what you will do, you do some kind of the linkage as you understand from the air quality modeling, and then we discussed last time and we developed the linkage between the sources and receptor was our Taj Mahal, and we said there were problems. Okay. And then you could say, well, we need to control something. Okay. Like you said, refinery must control the pollution, the area sources must control the pollutions. National highway, this problem is very serious. So then you can say that okay, needs to be controlled. But how to control? Now we will discuss, we are going back at the source, how to control the emissions at the source. Okay. One is you can take the preventive steps. Okay. You can change the fuel, right? Okay. You can increase the stack height, you can increase the exit temperature. Okay. That's all you can do. Certainly you can do that one, and sometimes we even try that. Okay, change the fuel. For example, lead was the problem, we changed the fuel to unleaded. Okay, and then similarly the diesel was a problem, we changed the fuel from diesel to CNG. Okay, so that step we take. But in spite of that, this is major decisions you have taken, but sometimes you have to have the engineering solution to control the things. Okay, similarly what you do in the water treatment and the wastewater treatment and things like that. So that another 2-3 lectures will be how to control, how to call for the engineering control at the source. Okay, not the preventive control, but the engineering control, how we can put certain devices that our pollution will reduce. Okay. So we can say what we are going to discuss is and first thing we will talk is the particulate. Okay. Whenever you want to remove something, okay, you need some force. Okay, you can't remove something. If I have to eject you from your chair, I have to use some force. Okay, so the force, so means for the control you need force. What is that force you apply in your water treatment? Gravitational force. Okay, so this can be a gravitational force. One can also apply the gravitational force in air pollution control. Okay, but this force, which I will show you with some little example, is not so effective, not so powerful, and we will say why it is not so powerful. Okay. So what we do, we apply another force, and then that we call as the centrifugal force. centrifugal force. And then we somehow, if we understand the centrifugal force, then we can apply it to remove the particle. Okay. So I want to do some small example. Okay. I want to compare the gravitational force versus centrifugal force for the removal of the particle. Okay. Let's see which one is larger and which one makes more sense. We are not talking about where the cost is involved is more. Always gravitational settling will be cheaper because you have to do nothing. Gravity is automatically working. You don't have to introduce any kind of outside thing to improve your force mechanism. Okay. So how do we do? Okay, let's compare the forces first. So gravitational force, F gravity if you like, is mg. Okay, and suppose I am providing a centrifugal force. Okay, so that force, okay, if I call it C, okay, what is that if you can recall? mv square by r. Everyone recall that? Okay. Let's see, call it C, okay, centrifugal velocity. Okay. Suppose I take the ratio of these two forces. Okay. So gravitational, or let's say Fc by Fg. This is a little concept, simple things, but that is what you should know more than more complicated things. Okay. If I say this one, that becomes Vc square by R by G. Okay. Suppose I am able to give the centrifugal velocity as 20 meters per second and maintain a radius of, let's say, R equals to 1 meter, taking G equals to 10, how big is this force compared to FGR? Please tell me. My Vc is at 20 meters per second. Okay. Take G equals to 10 and R equals to 1. 40 times. Okay. Just example to make you explain as to why we are looking for the centrifugal force. Okay. For R equals to 1 and Vc equals to, what we said, 20, right? Okay. So this ratio Fc is almost 40 times Fg. Okay. So it makes sense that, well, we should really apply the centrifugal force to remove the particle. Have you, all of you have heard the centrifuge which we use in the laboratory? What we are doing? We are doing the same thing. We are applying a large centrifugal force to separate the particles from the water. Okay, and then they quickly settle on the bottom, and then you decant it. Okay, and same thing, suppose if the centrifuge was not there and if you had to use the gravitational settling, maybe, and then you want to decant the thing, you have to wait the overnight for 24 hours. Okay, then you have to wait for a long time and hope everything will settle and things like that, and you don't have such time. Okay, okay, and suppose even if you had such time, our processes are continuous. If we have to make a water or air stable for that many hours, means the dimension required for the tank will be very, very huge. Okay. So that also is one of the constraints. Not only it may take time, but the dimension that you may require may be very, very high. Okay. So we apply, I am not saying that we don't use the gravitational force, but we apply the centrifugal force in the engineering control of particulate matter in air pollution. Okay. Same thing, let us see it from the point of the velocity through which they will be removed. Okay. So suppose if I take, this is my axis and this is what is my circular path through which I am providing the centrifugal force. Suppose I look at this point, okay, and this is my terminal velocity due to gravity part. Okay. How the centrifugal velocity, which direction it will act? It will try to throw it outside. Okay. So let us also call that as Vt C, and this is called Vt G. Okay. And where do I write my Vc? Where do I show my Vc? Tangentially here, right? Okay. So this is my we will see. Okay. Let us see, and then ultimately things decided by the velocity apart from the force. Okay. So, let us compare the VTG versus VTC. Okay. So, VTG, okay, terminal velocity due to settling. What is that? Which law is that governs that? Stokes law. How do we get the Stokes law? What are the forces applied on the body? Gravity, buoyancy and drag. Three forces. Okay. And when the three forces are in equilibrium, the particle attains a constant velocity because your acceleration is 0, because the forces are in balance, and you can find out this thing. And if you recall, this will be, because I recall it from my high school time, let us say if I can write G by 18 particle minus the medium, let us write this as P, particle mu. Okay, right? I have to find out the VTC. By VTC, same forces are acting, okay, but the additional, the gravity here, the acceleration, okay, if I replace the acceleration g here with the acceleration, I can get the same equation for the settling or removal velocity with the help of the centrifugal force. What is the g I should replace with? Look at this one and please tell me. What is the acceleration here? V square by r. Okay. So I can replace g and I can get what is the velocity of that one, simple thing. So if you agree, let us write here m, well I do not have to write m, we write V square by r. Okay. Again and the same expression. Okay. And suppose if I take r equals to 1 and Vc as 20 meters per second, okay, how large will be VTC compared to VTG? Particle diameter is the same, viscosity of the medium is the same, right? This is same, and then you see here, and Vc is I am taking this as the 20, okay, and you see the velocity will be how much time? 40 times if I take r equals to 1, okay, something very similar to what we got. Okay, you can really find out in terms of the meters per second square, meters per second, and then you see again the VTC is also very, very large. Okay, so then why do I not apply the force of centrifugal to remove my particles? Okay, and the devices through which we use the centrifugal force to remove the particle is, that is what we call as the cyclone. So the devices that uses the concept which we derived in a very, again very in a qualitative sense, the devices are called cyclones. Okay. And now I will show you a picture of typical cyclone, okay, so that I will save some time drawing that thing. Where are we? What I can do, I can introduce a high velocity tangentially, okay, and then this is my inlet, okay, and provide a tangential velocity. Okay. So what is the important thing to see is this is h of the inlet, this is w, that is the width, okay, it goes tangentially around this one, okay, and then there is the outlet here, and so this gases and the particles will have the circular motion. Okay. Okay. Once they get the circular motion, okay, what will happen? this picture, apart from the picture, I want to show you onto this thing. So I will not draw exact picture, but let's see. That's how the centrifuges work. So you are entering tangentially some gases. So gases will travel in the helical path, okay, and let's say the particles are sitting onto that one. See, let's say this is the particle, okay, and this is the particle, and let's say this is the particle, because all they will go along with the gases, okay. So that is what is the helical path that is being shown here, okay. If I talk about this particle, who will have more inertia, the gas or the particle? Particle has more inertia. So as a result, what will happen? Particle will continue to move in its own direction and leave the stream of the gases. So this particle, if we can continue with this thing, it leaves, this is the path of the gases. So this, because of this tangential velocity, it will come here and hit to the wall, and with the impaction it will stuck onto this one, okay. And same thing, okay, this particle, because of its own inertia, will continue to move tangentially, and then okay, and this is how the whole thing will go on, keep on going round and round. And then finally, when the gas is more or less clean, it moves back with the inner helical to go out, in and out, and this is clean. And you will see within no time, you see the particles depositing here, and then you have the layer of the particles here. Which they falls back into the hopper. These are the particles which can hit to this one, and then they fall if you shake it a little bit, or just because of the cake as it develops, it will fall here. Okay, and this is how is the mechanism through which you remove the particles. One of the ways to remove the particle is to have the cyclone. Okay. And that's what you see the picture. Okay. I'll just scroll the picture up and down, and okay, this is what you see. So, and of course also I'll send this one through the mail. What you see here, the conical section, the cyclone body, and things like that. What is, if I can, I'm just wondering if I can make it small and have the full picture. Okay, my dimensions are gone. Anyway, we'll correct that one. So you see, now you see the full picture, and this is what we call, this is the conical section, this is cyclone body, the gas outlet tube, this one here, the gas outlet tube, okay, this is the entrance, and what you see here, okay, this gas outlet tube is projected little bit inside, okay. If you don't inject it, here this particle, maybe just before they go for a circular path, they will just be sucked right here. So this thing is put little bit inside, okay, and this is what you get the dust collected here, and this is typically how the centrifuge work. So let me again, okay, and few things I want to tell you is okay, some of the dimensions you see here. D naught, well, these are important what I am saying. This is the diameter of the cyclone. And this is, you haven't mentioned, this is DE, that is the exit diameter. This distance, okay, not from there, because that is anyway that is connected somewhere, we don't know. But you see this distance to the outlet pipe must go inside the cyclone body is, where do I write? I didn't write, but take this as the S, okay. And then this is the height from here to the cyclonic body is H1, and the conical section is H2, okay. this diameter is dd, okay, and d naught and d this thing. So every dimension of which you see here, h, w, h1, h2 is defined in terms of the diameter of the cyclone. This is a standard practice and it works fine. Okay. So this is important thing is d naught, and rest of the things, that is h, w, h1, h2 and dd is defined in terms of the diameter of the cyclone, and this definition is like this. Okay. The w, that is width for inlet to ratio to d naught is 0.25. Okay. This is h, okay, to d naught is 0.5. What was h? The height of the inlet, okay, the height of the inlet. Suppose I am coming with a pipe which is tangential, this height, okay. The h by d naught is 0.5, and h1, that is the cyclone body, to d naught 2 times. h2 is the conical section, you see here, this is h2, is again 0.5. S is the pipe, how much inside it should go into the cyclone to avoid the short circuiting. So that is what is S, is 0.625, and that is DE, that is the outlet, okay, is 0.25, and the bottom one, which is also important, is this is a DD, you see here, this is DD, is 0.25. It is kind of fixed dimension. So you simply, somehow you should come to know about the D naught, that is what is the diameter you want, rest of the dimensions are fixed. And I am sure you must have seen some cyclone somewhere. Okay. So that is how the cyclone works. Let us little bit talk about a little bit more maths or theory of this one. Okay. Okay. This is what we have defined here, the cut diameter of the cyclone. Cut diameter means the particle diameter that will be removed with 50% efficiency. Okay. That is how the cut diameter is defined. Because why we define the cut diameter is that otherwise we cannot define the diameter, because you cannot guarantee that something will remove with 100% this thing. So if I say here, if I draw a graph to explain you what exactly the D cut is, efficiency of removal, and I take D, the diameters, which particle will have the various diameter. This is 1, means 100% removal, okay. Then you see here, this is 50% or 0.5 if you like. This is your D cut, or in the literature you will find this as 5. Okay, and that is what is important for us, as to we want to find out with what particle it will be removed fully. Okay, and I will explain you the terms which are there. Okay, see here, the particles which are larger than this will be removed like 99%, 98%, and particles which are smaller than this one, they will remove with a smaller efficiency. Okay. Have you seen our high volume sampler or respirable dust sampler? You have not seen. Okay, doesn't matter. So you want to see, so that's how normally for the cyclone we don't define the particle that will be removed 100%. We said that what is the efficiency is defined of the system of the cyclone, is that what is that diameter which will be removed with completely with 50% efficiency. So here this particle, this diameter, as you see, will be removed with 50%. Larger than this will with the higher efficiency, and the lower one then is the higher efficiency. So now let me explain what these terms are. Well, of course, W is what? The width of your tangential pipe which is going to this one. Mu is the viscosity of the air. Okay. Vc is the speed that you could give inside, okay. Rho particle is the density, okay, and n is the number of turns that the gas stream could make. So you see here the number of turns of the outer helix. Okay, don't be confused with the inner helix. Inner helix, the turns will be much larger. Okay, we have the outer helix in the cyclone, so that number of turns that it can make. Okay. You will not have the calculators, but okay, let's discuss the same thing further. So, if you have decided this is W, you know number of the turns it will take, okay, you know the velocity that you are giving, you can find out the D cut, okay, alright. Should we do an example or? Let's see if we can quickly do it. Let's say I take that as the 0.25. That is my width. Okay. Mu is how much for air? Okay. Suppose I am able to give the 5 turns, okay, rho particle, let's say 2 grams per meter, 2 grams per cc, okay, so I can write this as 2000 kg per meter cube is a rho A, and I have to have the Vc, and let's say Vc, I have to have the Vc2, so this is 20. Okay, I repeat, W mu Vc 2 pi, number of turns 5, and the particle density as 2000 kg per meter cube. Can we somehow do it quickly, or it will take some time? 1.13 into 10 to the power minus 4, right? Correct? Okay, this is meters, very good. So this is my D50 of this design which I am talking about, and then so I can convert this into micron. That's generally what we measure the particle size in microns, right? So multiply this into with 1.13 10 to the power minus 4 times 10 to the power 6, so that becomes micron meter, and that will be your 1, something like this. Okay. This is really a hypothetical number I had taken, okay, but generally, okay, we are able to comfortably remove a particle with the size about 5 micron, okay. Obviously, this I have taken this as small, 0.25 meter, this velocity could be increased, but so you can see that, well, depending on the variables, we can go something like 5 micron meters as the particle that can be comfortably removed. But then I must define what I mean by comfortable. Okay. So let's see what is the comfortability of the system, if you like. Okay. So let's see the comfortability of the system. Okay. What is more difficult, to remove the larger particles or smaller particles? The smaller particles is always a problem. Okay. If I want to remove the smaller particles, I must bring my D cut down, right? Because I want a small particle. If I want to bring the D cut down, okay, what are the control variables I have? I can't control mu, I can control W, I can control N, but there is a limit for N because this will become too large. I can control Vc, I cannot control the rho particle, okay. So then what we are talking in terms of the comfortability or the particle size that can be removed. Particle size that can be removed. So options are increase the W, increase or decrease? Decrease. bring it down, okay, or increase the C, okay, and suppose n is constrained because of the length. Okay. So what do? I can decrease the W or increase the VC. Okay. I want to define something important which you will need to understand, at least in qualitative sense, is a pressure drop across the system. Okay. So before we see which we have the better option, this is a better option or this is a better option, we need to define the pressure drop. Okay, which is delta P across the device. Okay. To just give you a feel, if the pressure drop is high, okay, what it means to you. Suppose there are two devices, one is having high pressure drop, another is having the low pressure drop. VC will be very, very high if the pressure drop is high. Okay, that argument we agree. But let's not get into the VCs and things like that. I have a system. Okay, leave beside we have a cyclone or something. We have a room. Okay, or we have to do the ventilation part. Let's forget about cyclone. And then I have the pressure drop in the room as the fluid travels. There will be a pressure drop. If the pressure drop is more, okay, and I want to maintain certain velocity, okay, it means if the more is the pressure drop, more is the fan I will need to force the air through the system, right? If the pressure drop is more, okay, then I should need more powerful blower to blow my fluid through the system. Okay, if my blower capacity is more, okay, it means my blower is more and the power requirement will be higher. Okay. If the delta P is high, it means I need a huge blower, okay, correct, and my power requirement will continually go up. And we will talk at some other point, but generally delta P is proportional to VC square. Okay. So if I decide in my system that I want to improve my or I want to decrease my D cut, so I can increase the VC, but I can't increase VC too much because otherwise I will need a very huge blower, okay, and my pressure drop is high. Pressure drop is high means my cost of running the equipment will be high because my power requirement will go high, okay, and which is of course in industry or wherever you are, the cost of power is a major consideration, okay. Size of the blower is a major consideration, okay. So generally with this choice, okay, is not good generally. Okay, so then I am left with the choice is this. Left with the choice is that I can decrease W. Okay, if I decrease W, okay, what happens to my cyclone? And I want to maintain same VC by the way, okay, because I am not handling the VC I don't want to change, okay. If I reduce the VC, then again my D cut goes up. So this I am keeping constant and W I am reducing, then my cyclones become small, right. Then it means I should have lots of cyclones, okay, to maintain the same VC and reduced W, okay. And that system where we apply this concept, okay, where we are reducing the W for the same VC, because VC we don't want to disturb because the pressure drop thing, so such system is called multi-clones, okay, because multi-cyclones or multi-clones, okay. And then by virtue of going multi-clones, I can reduce the particle size to still a reasonable extent, okay. And remember that I have more cyclones placed, but I am not increasing my power requirement, nor I am increasing my blower capacity, okay. So that is what is a thing, well, something you will see I am sure here. The same thing which I talked to you. So that we have agreed, and that is what you see is, I am sure I can show you the picture, is the concept of multi-clones. Here we have many small cyclones. Okay. So here what you see here is that earlier we were only designing one. So now what we do is we can design many of the cyclones. Okay. VC we can maintain same, because VC we don't want to play with VC, and you see here, if you go here, the W here which is in some other form, see somehow you have to introduce the tangential velocity. You can cut the vanes rather than provide the tangential. So you can cut the vanes and then you come here with the, and you get the cyclonic motion, fly ash or whatever the particles are removed, and this goes off. Okay. And then what you see here, the dirty air is introduced somewhere here. Okay. And the whole thing is filled with the dirty air, and then since it is tightly packed, the dirty air will be forced on to enter into each of the cyclone, and then the clean air go up, and the outlet of the clean air will be outside this ceiling. So you see here the outlet will be here, outlet will be here, outlet here. So the clean air goes out. You understand the concept? Okay. So we have such things we call as the multi-clones. Okay. Small one. Okay. But there is only little problem. Okay. What is the problem? An important thing, and you should write and understand, is the pressure drop across each of the little cyclone that you see should be the same. Okay. If some cyclone has this little lesser pressure drop, wherever there is less pressure drop, all air will go through that one. See, wherever the pressure drop is less, it means there is an open area. Okay. And the fluid will like to follow the path of least resistance. Okay. So then one of the cyclone will be loaded heavily, and the others will not get the gas going through this one. So that becomes a little tricky, that you have to somehow ensure that the pressure drop across each of the tiny cyclones which you see is the same. That is the key for the operating multi-cyclones. Okay. Maybe you will not find so much details in the book, but still you can read, but the concept is like this. So they have some mechanism which is some kind of thing that they can measure the pressure drop across each of this thing, and they have to maintain the same pressure drop. Maintaining the same pressure drop means what? Maintaining the same VC. Okay. Maintaining the same VC, and you have to have identical dimensions. Okay. You can't have one cyclone bigger and another smaller and things like that. Okay. And this thing you will find many plants. Okay. Whether this is air pollution thing, or you are just cleaning certain things within your industrial processes, this is very commonly used. Okay. So you got the concept of the multi-clones, and the reason why we need to go to multi-clone, and why we need to maintain certain thing in the multi-clone to ensure that it functions properly. Okay. Okay, then I want to come to something else. But there is a limit to which you can do. Okay. Then again, we should think of applying some more force. Okay. Centrifugal force will work up to some level, but you see we encounter in the combustion processes and many other processes the particles even in submicron size. Okay. Particles which could be 1 micron, 0.5 micron, 0.2 micron, and they are more dangerous than the particle. So if you are having the particle size larger, okay, you should go ahead with the cyclone and be happy, but that's not the thing. So we sometimes one of the force that additionally we applied is electrostatic force, additional force, or well, we'll see, we call it additional force. Electrostatic force to remove smaller particles. Okay. Let's make some physics of this one. Why electrostatic force would be a better thing to do? Suppose in general again, we are not talking about the ESP. I am driving the particle to come and get removed. Okay. I apply various kind of force. Okay. One force was your gravitational force or centrifugal force and this thing, and there is a particle which is resisting. Okay. He doesn't want to come with this one, or there is someone stopping him to be removed. Okay. That's normally is a drag force. Okay. Okay. If that is the drag force. So drag force, let's try this one. I'm just say if I can try it. The drag force in terms of the diameter, because we are focusing on the diameter. So drag force is proportional to diameter of the particle. Okay. If I say the driving force, which may be the gravitational force or centrifugal force in diameter, what is that? What is the diameter? Square of the diameter, or square root of the diameter, or the cube of the diameter? Mass is the same. Okay. It's the cube, right? You agree? Or so this is d cube. Okay. This is d cube, because whatever force you take, there is a mass. Mass is related to what? More is the mass. Okay. Then this is related to d cube. Okay, so it means this is proportional to d square. In the case of electrostatic force, this is more like a surface phenomena. Okay, so this thing, this ratio of this driving force to resisting force, and this is surface phenomena, electric charging, electrostatic thing, is d square by d, that is d. So if I want to enhance this force, okay, when I am going to the smaller particles, okay, my diameter will reduce by the square. Okay, because I am going from higher particle to the lower particle. So if my diameter is reduced, it means my driving force is reduced effectively. You see, because this will reduce with the square of the diameter, right? My d has become, let's say, now 0.5. Okay, so this force, this ratio will be 0.5 into 0.5 is 0.25. Okay, 0.25. Okay, and so it means my driving force is like 0.25. And suppose I am using the electrostatic this thing, and if I have gone d from 1 to 0.5, how much is the driving force now? Proportional to 0.5. My d is become 0.5 d. So my driving force is 0.5 d, and here the force was reduced to 0.25 d. So it means if I go with the concept of the electrostatic precipitators, I can, with the same force, I can reduce much smaller particles. Okay. This, see, the mathematics part, writing equation design, is of course you can even do with the handbook. Okay, but this is what you have to understand. Because if I use the electrostatic force, okay, then I can even go on to the smaller particles, and I will still have my driving force which is more compared to my gravitational settling or centrifugal settling. Because my driving force will reduce here with the square in the diameter. From d, whatever my force was there, I want to go for a half of the size of the particle. This force is 0.25, whereas here it will become only 0.5. And when I go smaller and smaller, this thing become more and more meaningful, that we go for the electrostatic force and then use the electrostatic force. Okay, you understand? those of you have not understood why this force is proportional to dq. See here, because I saw someone quite blank onto this one. I am making the concept why the driving force was dq. mg for example, m I can write this as rho vq, rho times v I can write, suppose it is a sphere for example, 4 by 3 pi r cube, which is nothing but dq. So that is where the dq has come from. Oh, I am sorry. Okay. So now is this point clear, that why did I write dq here? Okay. So this point is clear. So we can use electrostatic force, and the system that uses electrostatic force, okay, to remove the particles of the smaller, once we are interested in removing very small particles, we apply somehow the electrostatic force, and the system that, or the device that uses this thing is called electrostatic precipitators. Okay. So that device which will use more, and this one, the electrostatic force will be a surface phenomena. Okay. So we will be discussing, I don't know, in the next class. Okay. The electrostatic precipitator, it looks something like this. I will explain you from inside what it is. Okay. You see here, it is the dirty air that goes in there, and I am not sure if you can see, there are multiple plates, I don't know, and within the plates there are gaps. Okay. So this dirty air goes through them. Okay. So just to make you understand, I will draw two plates and comparatively much farther distance. Exactly, I am drawing the same plates but in 3 dimension. And your air is entering from here. This is the dirty air which is entering between the two plates. Okay. And within the plates, what you have is, you have a charging electrode. So there is if I have a rod here and which has a wire, okay, and that wire, if the wire hangs like this with a heavy weight here, there is something like this between the two plates, there is a pendulum which is hanging, okay, that you cannot see here. Okay. So there is some pendulum which is heavy weight, so that it can stand. Okay. And these plates are grounded. Okay. And then you apply a voltage, a DC voltage, okay, across the plate and the charging electrode. Okay. So this what we call as the collecting plate, and this one charging electrode, and voltage that is applied is of the order of 40,000 volts. Okay. And it is a DC voltage. Okay. It is a DC voltage. Now what happens? Once it comes through this one, these are some and this, and generally this is negatively charged, generally. This charging electrode is negatively charged. Okay. And you will see there will be, if we see from the inside, there will be, if I can change the things here, let's see. Okay, let's take the blow up of that thing. Okay, so here I think we'll stop it here.